Okay, next we will discuss the intrinsic carrier concentration, which we represent by Ni. As we know that an intrinsic semiconductor, if one electron jump from valence band to conduction band, then there will be a hole created in the valence band. If another electron jump from valence band to the conduction band, then another hole will be created in the valence band. So at T is equal to 0, the valence band is completely filled while the conduction band is completely empty. But if we increase the temperature, then electron will jump from valence band to conduction band, and during this transition from conduction valence band to conduction band, a hole will left behind in the conduction band, valence band. So if suppose another electrons jump from valence band to conduction band, then there will be another hole left in the valence band. So it means that an intrinsic semiconductor, the number of electron in the conduction band will be equal to the number of hole in the valence band. If three electrons present in the conduction band, then there will be 3 holes in the valence band. So we can say that number of electron in conduction band is equal to number of holes in valence band. In other words, we can say the number of electron in the conduction band is represented by N, which is equal to the number of holes in the conduction valence band, which is represented by P, which is equal to Ni. I represent this by Ni, and this Ni is called intrinsic carrier concentration. Carrier concentration. Now the product of number of electron and number of holes will give us the Ni square. Ni square is equal to Ni times Ni. So Ni is equal to N, or Ni is equal to P. So Ni square is equal to Np. This is equation number 1. Now in the previous videos, we calculate N is equal to Nc into exponential of minus Ec minus Ef over Kt, and P is equal to Nv into exponential of minus Ef minus Ev over Kt. Using these two values, where Nc is equal to 2 into 2 Me steric over h square whole 3 by 2 into Kt whole 3 by 2, and Nv is equal to 2 times 2 into mh steric Kt over h square whole 3 by 2. Using these values, Ni square will be Nc e raised to power minus Ec minus Ef over Kt times Nv into e raised to power minus Ef minus Ev over Kt. Ni square will be equal to Nc Nv e raised to power minus Ec minus Ef plus Ef minus Ev over Kt. Now plus Ef cancel with minus Ef. So Ni square will be equal to Nc Nv e raised to power minus Ec minus Ev over Kt. Ni is equal to Nc Nv square root into e raised to power minus Ec minus Ev over 2 Kt. Now if we look at this picture, then this gap between conduction band and valence band is called energy gap, which is represented by Eg, and this is equal to, if we subtract Ev from Ec, we get this gap. If we subtract Ev from Ec, we get this gap. So instead of Ec minus Ev, I will put Eg. So Ni is equal to Nc Nv exponential of minus Eg over 2 kT. Now using the value of Nc and Nv in this expression, which are given by this, and rearranging, we finally get the final expression is Ni is equal to 2 times 2 pi kT over h square whole 3 by 2, and we have me steric mh steric whole 3 by 4, and we have e raised to the power minus Eg over 2 kT. Or we bring this t from this factor, so we get Ni is equal to 2 times 2 pi k over h square whole 3 by 2, and we have me steric, and we have mh steric whole 3 by 4. So we have this t whole 3 by 2 e raised to the power minus Eg over 2 kT. Or this is independent of temperature, so this is a constant value for a particular material. So instead of this, we will replace a constant factor, which is A, and we have t whole 3 divided by 2, and we have e raised to the power minus Eg over 2 kT. Now the final expression, which I will write it again, is Ni is equal to A into t whole 3 divided by 2 e raised to the power minus Eg divided by 2 kT, where A is equal to 2 times 2 pi k. So here I forgot the, no, yeah, 2 pi k over h square whole 3 divided by 2, and we have me steric effective mass of electron into effective mass of hole mh steric whole 3 divided by 4. Now if you look at this equation, okay, then Ni is strongly depends on temperature. It depends on temperature. The temperature is here, and it's also in the exponential factor. Now A is a constant. A is a constant, but it depends on the effective mass of electron in hole. It depends on the effective mass of electron in hole. Now the effective mass of electron in hole is different for different material. So this means that this factor A depends on materials. Now Eg also, Eg, the energy gap, this factor Eg also depends on material. Depends on material. Like different material have different energy gap. For example, silicon. For silicon, the energy gap is 1.1 electron volt. If we consider germanium, then the energy gap is 0.66 electron volt. From this, we can say that this Ni depends on two factors now. Ni, the intrinsic area concentration, depends on two factors. Number one, temperature, like how much temperature we are dealing with, or how much temperature, how much is the temperature when we are studying the material. And the second one is nature of the material. Nature of material. like what kind of material we are using, what kind of material we are using. Now consider at room temperature like T is equal to 300 Kelvin or 27 degrees Celsius. The band gap and carrier concentration for different materials are, suppose we have different materials in germanium, we have silicon, and we have gallium arsenide, which is extrinsic material. Yeah. So we have here we have the energy gap Eg, and here we have the carrier concentration, means number of carriers per centimeter cube. The value will be this. Now gallium has energy gap 0.66, so this energy gap is in electron volt, and the carrier concentration is 2.5 into 10 raised to the power 13 per centimeter cube. Now the energy gap of silicon is 1.11 electron volt, and the carrier concentration is 1.5 into 10 raised to the power 10 per centimeter cube. Here the gap is 1.43 and the carrier concentration is 2 into 10 raised to the power 6 per centimeter cube. Now from this table we can say that if Eg is increasing, the carrier concentration is decreasing rapidly at room temperature. So this is all about intrinsic carrier concentration. Thank you.